Today, I want us to look at the various ray diagrams and cases for refraction in lenses, curved lenses, specifically our converging lenses and diverging lenses. The converging lenses are also known as convex lenses, and the diverging lenses are also known as concave lenses. Okay, so concave, so these are concave lenses because they cave in. This is a biconcave, caves in at two ends. And then these are our convex lenses or converging lenses. So we're going to look at the various cases. All right, rays from object at infinity. Mostly we need just two rays, two lines. Okay, one going when it hits the lens, it bends, okay, and then the second one bends. This one's coming from very far away, so it bends, and then the second one just goes right through the center of the lens. Okay, so where they meet, you have your image formed. So the object cannot be seen because this is the first case. Object is at infinity, very far distance, like looking at an object from space. Okay, you can see the object is inverted and is formed at the focal principal focus. Okay, F is for the principal focus, C is for the center of the lens. All right, now when the object is at twice the focal length, remember 2F is 2 times the focal length. F from C to F is our focal length. So when the object is at twice the focal length of the lens, you see one ray passes straight through the principal focus on the right side, and then the other ray goes right straight to the center of the lens. So where they meet, the image is formed. You can see the image is likely going to be the same size as the object. Let's look at object greater than 2F. Okay, I should have come. So object greater than 2F, one goes right straight to the lens, but it must pass through the principal focus on the right side of your lens, and then the second ray goes right straight to where they meet. You have an inverted and real image also. This time it's between F and 2F. This case, the object is at 2F, image is at 2F. This case, the object is exactly at the principal focus. And if the objects are principal focus, you see the rays don't come together, so the image is not formed. Okay. All right. What of when the image is, okay, just like I said, the image, when the object is at the principal focus, the image is not formed. See, the two rays do not come together, right? And so the image is at infinity, it's not formed. Now, what if it's closer between the principal focus and the center of your lens? You see the rays do not come together on the right side. Instead, they come together on the same side as the object. So this is the object and this is our image. So it's a virtual image. That means the image cannot be formed on a screen. It's virtual, so we use dotted lines for that. So you see the image is virtual and magnified. So this is the only case in the convex lens where the image is virtual. What I want to point out, like you notice that we mostly use just two rays. One that is refracted through the principal focus on the right side of your converging lens, and one that goes straight through the center C of your lens. So where these two rays intersect is where your image is formed. Okay. Now look at for the concave or diverging lens. This is your object R. So it comes like, and it diverges, like it spreads out. Okay, bends it away. So bends here, and then one goes straight to. So it has to be the back trace. The back trace of this line, where they intersect, is where your image is from. Virtual. Let's have a summary. So a summary of all the positions or cases for refraction in a lens. All right. For image formation by converging lens. Case 1, where the distance, DO stands for the object distance, is greater than twice the focal length. The image is likely going to be inverted, real, and diminished. Right. This is the configuration for a camera. Okay, here the focal length of the lens system of the camera must be adjusted for a particular object distance. Okay, so that the image distance DI is at the location of the film. All right, so just to recap, when the object distance is greater than the radius of curvature, twice the focal length is called the radius of curvature. The image is inverted, real, and diminished. Now this is the configuration for a camera. Okay. Now another case, the second case, if the object distance is between the principal focus and the center of curvature. Between focal length and radius of curvature, the image is real, inverted, and magnified. Okay. Now this is the configuration for a projector. Okay, a projector, since you normally want the real image on the screen to be upright. So for the object distance that is greater than focal length but less than twice the focal length, you have this case. This is the case you are looking at. Yeah, so the object is greater than 2f, it's greater than f but less than 2f. So you see the image is real, inverted, and magnified. The image is real, inverted, and magnified. Now this is the configuration for a projector. Okay, since you normally want the real image on the screen to be upright, where the object, okay, the object on the film or slide is placed upside down in the projector. Okay, so these are the cases. So this is the case for projector. Now when the the focal length is greater than the object distance. All right, so where you have the focal length greater than the object distance, okay, this is the case, the focal length greater than the object distance. So what do we have? The image is virtual. It's formed on the same side as the object. It's virtual. It's magnified. Okay. See, it's signed so, and it cannot be formed or placed on a screen. Okay. So the image is virtual and it's formed, is upright and magnified. This is the configuration for a magnifying glass or hand lens or a simple microscope. All right. The image is virtual, upright, and magnified. Okay. All right, so quickly, I want us to look at a summary of the sign convention for lenses. The focal length is positive for a converging lens. Take note of that. The focal length is negative for a diverging lens. Okay. Now, the object distance is positive if the object is to the left of the lens, and the object distance is negative if the object is to the right of the lens. Okay. This could occur in the case of when you're imaging with more than one lens. If you're imaging with more than one lens, that's when the object could be to the right of the lens. Okay, but mostly your object is usually to the left of the lens, and your image is okay. Image could vary. Now the image distance, DI stands for the image distance. All right. So this is a summary of the sign convention for lenses. So it's quite helpful for us to know how to calculate, okay, object distance, image distance, focal length, and all that. So usually you use U for your image object distance, and we use V for the image distance. I just like to use DI. DI, okay. So image distance is positive for the image formed on the right side. So all images formed on the right side of for a converging lens or any lens at all is real, while the images formed image distance is negative for image formed on the left side. So images formed on the left side are virtual. So that means diverging lenses are virtual images. All right. So in summary, M, this is a symbol for magnification. Magnification is positive for an upright image. Magnification is negative for an inverted image. All right, so this is the case for most converging lens images. Okay. Okay, so that is magnification. Remember, your magnification equation is height of image over height of object, or distance of image over distance of object. So now let's look at eye defects such as hyperopia. Hyperopia is also known as hypermetropia, which is basically long-sightedness. And long-sightedness could be a case of a shortened eyeball, and in this case, the near point is usually greater than 25 centimeters. All right. Okay. So hyperopia or hypermetropia is long-sightedness. The near point in this for a long-sighted person is usually greater than 25 centimeters. Okay. Now, because at maximum accommodation, the formed image is behind the actual retina, and hence is blurred. Okay, so the image forms behind the retina for a person with long-sightedness. Okay, that's for his near point. Okay, so you cannot see his own near point is greater than 25 centimeters. All right, so things at 25 centimeters tend to appear behind his retina. Okay, so how is the correction? How do we correct hyperopia or hypermetropia or long-sightedness? A converging lens is used. A converging lens forms a virtual image at the eye's longer near point. Okay, remember the person with a long-sightedness has a longer near point. Near point is greater than 25 centimeters. So what you do is use a converging lens which will form a virtual image at the eye's near point. This image acts as the object for the eye and is what the eye actually focuses on. Okay, so it's something like this. All right, so it forms a virtual image. So this is the lens. So this is what the type of lens that is used. All right, so like I was saying, this is the type of lens which is used for to correct long-sightedness. Okay, so this is the image is formed. This is the correcting lens. So it forms an image at a further point. So this image becomes the object for the eye, for the natural lens of the person with a long-sightedness. Okay, the object must be within the focal length of the converging lens. The object must be within the focal length of the converging lens. Okay, so that is hypermetropia or long-sightedness. So let's look at this question. Sanjay has hyperopia. This is basically long-sightedness. The near point of his left eye is 150 centimeters. Okay, normal near point is 25 centimeters. Take note. What prescription lens will restore normal vision? What prescription lens will restore normal vision to Sanjay? So note, the image of spectacles must be formed at the eye's own near point of 150 centimeters as against 25 centimeters. Okay, so the image is now minus 150 centimeters. It's negative because it's a virtual image, so you have to put minus. Take note of our convention. Remember, now the object is at its 25 centimeters normal near point. So, like I said, the image of spectacles must be formed at the eye's own near point of 150 centimeters. So this is Sanjay's own near point. The object is at 25 centimeters normal near point of a normal eye. Okay. Now, remember your formula, your mirror formula. Principal focus is focal length rather is equals to u times v, where this object distance, image distance, all over the sum of image distance and object distance. So slot in those values, and then you have that the focal length is going to give you 30 centimeters. So this is what the diagram looks like. This is the length, this is the object distance, and it is projecting the all right, so okay, just to point out very quickly that look at this is negative because this is a virtual image. This is the case, like I told you, this is what we are looking at. So the image is virtual. It's a converging lens, quite all right. Converging, or also known as convex lens. So this is the object at 25 centimeters, the normal near point. But for a long-sighted person, you have to push it backward to 150 centimeter for Sanjay in this case. So this is the image that is formed. Now this image becomes the object for the Sanjay's normal eyes, okay, or Sanjay's long-sighted eyes. All right. So in summary, a converging lens, thus a converging spectacles of focal length 30 centimeters will correct Sanjay's long-sightedness. All right. So this is the image. I mean, this is a picture for this question. Okay, Sanjay has this is his own near point. This is Sanjay's near point. He has long-sightedness, and this is our normal near point of a normal eye, 25 centimeters, and that's what happens. So this is converging spectacles of focal length 30 centimeters will correct Sanjay's long-sightedness. So next up, we're going to look at short-sightedness or myopia.